astronomy kids. Mr. Johansson here. We are doing question number 12 today. And that is, how does a star produce energy? Why does the strong force make so much energy available? Well, let's talk about it. We're going to be talking about then how stars actually work. So in order to really get an idea of how stars work, we have to look at the conditions at the spot in the star where it's actually making the energy available. So where is that? That's in the core of a star. And in the core of a star, we know a couple things about the core of a star. So in the core, there are basically two conditions we really have to consider. These are important. First is it's hot. Okay, so what does hot do? Right? Well, hot is just how fast the atoms are vibrating. But it's so hot inside a star that the atoms are ionized. They just shake it so fast they shake their electrons off. Now, what atoms are we mostly talking about here? Hydrogen atoms. These are the ones who are going to be playing here. So hydrogen atoms are ionized. Now, if you ionize a hydrogen atom, well, a hydrogen atom is just a proton and an electron. You rip that electron off, so these are naked protons. Positively charged, naked protons. All right? And because they're very hot, they can vibrate. They're vibrating, and they can get close to each other. They're vibrating so fast they can actually approach each other. Now, what's holding them back from just typically approaching each other? Well, they're both positively charged objects, so they are repelled by each other. And the closer they get, the greater the repulsion, up to a certain point. What else about the star? Well, the other thing is that it is dense. How dense? Very dense. That, again, makes the naked protons very, very close together. That and the heat combined make them able occasionally to get very, very close together. And here's the thing. When they get very close together, another force comes into play. Here we have the electromagnetic force repelling them. But if they get close enough, a force 100 times stronger than the electromagnetic force, which is already enormously stronger than something like gravity, takes over. These protons then suddenly experience a tremendous force pulling them together. What's going to happen? Well, as they get pulled together, they slam into each other and release a tremendous amount of energy. This is the short form of this idea. There is a more extended idea we've modeled, and we know how this really works. That idea is called the proton-proton chain, and in larger stars called the CNO process. So we have the details of this, but the easiest way to understand it is to imagine this paper clip. See this paper clip? Tiny little paper clip. If I drop it to the ground, it's being pulled down by gravity. It's not being pulled down very hard. But if I were to drop it, and on the way down, it suddenly has a mass 100 million times greater. Okay? I liken it to this turning into the mass of an aircraft carrier. And I drop it. Well, it suddenly has, in this little paperclip, the mass of an aircraft carrier. When that hits the ground, it's going to, it'll pulverize the school. It'll send seismic waves out. So much energy will slam down, and you have to remove that energy. If you don't remove the energy, what's going to happen? Well, if you don't remove the energy from something, see the bouncy ball? Bounces. Ooh, bounces all over the place. The bouncy ball bounces because you didn't remove the energy from it when it hits the ground, so it's out of there. these protons, when they fall together, the energy is removed so that the protons can stay together. Now, how do we remove the energy? Gamma rays. The only option a nucleus has is by releasing a very energetic photon of light, in this case, a gamma ray. Gamma rays are so much more energetic than X-rays. So these protons falling together, when they get close enough, the strong force pulls them together and pulls them together so violently that, bam, some of that energy comes away. Here's an important consideration. You would think I would need 2 protons to make helium, but if you look at the structure of helium, it's really 2 protons and 2 neutrons. So 2 of the particles that fall together in the center of the sun, it takes 4 naked protons to make 1 helium nucleus. Now, they shoot off the excess positive charges in positrons, which is the antimatter version of electrons. Those positrons are immediately merge with an electron and completely annihilate each other, turning matter into energy. According to the equation, E equals mc squared, which is to say a tiny bit of matter becomes an enormous amount of energy. So in the sun, you'd see 1 plus 1 plus 1 plus 1. Well, these are 4 naked protons. You might be tempted to say that equals 4, but it doesn't. It equals something, I think, more like 3.95. Now, these are atomic mass units. Missing energy. Missing matter. And what does missing matter become? Energy. So, if you look at the sun or stars, this is why they shine. They shine because hydrogen is being converted into helium. And a nucleus of 4 hydrogen atoms weighs a little more than the nucleus of the helium atom they create. That missing matter, and in our sun, it's 4 million tons of matter every second disappears completely and is converted to energy. That's why our sun is so shiny. That energy from the core takes upwards of hundreds of thousands of years to eventually reach the surface and then spread out into space as light. But that's how all stars work. Based on the equation E equals mc squared and the fact that the strong force is binding matter together. So if you think about it a little bit more, you look at the periodic table of elements, there's 92 naturally occurring elements there. The universe started with hydrogen, and some of that was immediately converted into helium. That's it. After the Big Bang, there was hydrogen and helium. Where did we get all the other elements? Only in the core of stars. Stars can produce, through normal slamming together called fusion, all the elements up to iron. But when you add stuff together to try to make iron, it doesn't work the same way. You require energy in order to fuse stuff heavier than that, instead of giving off energy. So iron is the tipping point. Once you get to iron, a star cannot make any more energy in its core. And actually, when a star starts producing iron in its core, it has about 5 hours of life left. And then, once the core is mostly iron, it has no energy source anymore. And the whole star collapses and then explodes. It's the most titanic explosion since the Big Bang, a supernova. So all of these things are tied up. This idea of how stars produce energy in their core, E equals mc squared, that they can only produce energy from making lighter elements into heavier elements, and the heaviest element they can make in normal processes is iron. All the elements after that are made in some other fashions, where as the star explodes, huge numbers of neutrons slam into other atoms and make many of the heavier elements. We've recently discovered some of the elements are made in even more bizarre situations, like neutron star collisions. So it gets pretty interesting. But those shiny stars and the matter you're made of is the exact same idea. It's simply the end point. Stars making heavier matter, when they explode, give off all that matter into space, enriching space with all this heavier matter. So when our sun formed, it was many generations of stars that had already come and gone, seeding the space with all these heavier elements, many of which are used to make us. So that's a quick understanding of how a star produces energy. E equals mc squared. And the strong force is 100 times stronger than that electromagnetic force, 100 million times stronger than gravity. These forces, we still don't understand where they come from, why they work the way they do, but we sure do understand that they are here and they make the world we see. Hey, thanks astronomy kids for watching. Have a great day.